Welcome back to Tutorial 3. So far today, you've been using data from one specific CMIP6 model. But CMIP is a model into comparison project, and there are actually dozens of Earth system models that go into CMIP. And in this tutorial, we're going to be asking why are there so many Earth system models in projects like CMIP? Well, the main reason for this is that these models get developed by specific institutions who have their own science goals and development teams. And in fact, there are over 30 institutions that contributed to CMIP6, some of which have more than one Earth system model that they develop. And these institutions often have the infrastructure to run and maintain these models, the supercomputers required for that process. And you can see a map of these institutions up here at the top, which shows the number of contributing institutions to CMIP6 from each country. And while there are a large number of countries that contribute to CMIP6, there are many more that don't. And one area of growth that I would love to see in future CMIP iterations is to see the entrainment of more of these international groups into model development through the building of infrastructure and through the building of more collaborative networks like the ones that could be developed through Climate Match Academy. Now, what this leads to is differences between the actual code of Earth system models. And we can think of those differences in terms of the three ingredients we've already discussed today. So in terms of discretization, we've seen how time steps can affect the solution of a model. And we've also talked about how different models could have different grid geometries and resolutions. So the CESM model that you worked with yesterday and TIE-ESM1, which you've been working with today, had different grids. And that can lead to slightly different solutions. They can also differ in their physics, particularly through their different parameterizations. And they can differ in their algorithms and numerics. So there are multiple ways that you could put the same physics into a code that a computer could solve and evolve. We're not going to talk much about the algorithms today, and we've already talked about discretization in tutorial 1. And so we're going to focus in this tutorial on the physics aspect, the parameterization choices. Now, as a recap, in the climate modeling day, you got introduced to parameterizations. So processes that a model can't resolve or are too complex for a model to include must be parameterized if they're an important process for the climate scales that the model is simulating. And a parameterization basically approximates a physical process through its important parameters without modeling the actual process. And you've encountered a couple of examples of parameterizations in your climate modeling day last week. So one of the things you did was you constructed a simple energy balance model that estimated the effect of the atmosphere on outgoing long-wave radiation through a single parameter tau, the transmissivity. But this tau parameter was actually trying to approximate much more complex physics, so the absorption of different wavelengths of radiation by different gases, which could be distributed differently with height in the atmosphere. And so this was a parameterization for those much more complex vertical structure and different gas distribution effects on radiation. Another example was when you constructed and used this radiative convective equilibrium model, or RCE model, where we talked about how vertical motion caused by warming of air at the surface can effectively and efficiently mix heat upwards in the atmosphere. Now, the model that you used didn't resolve that vertical movement of heat. Instead, it looked at the lapse rate, and if the lapse rate looked like it was conducive to convection and vertical mixing, then it would mix that vertical column rather than moving air from one place to another. So that was another parameterization. Now, what kinds of things need to be parameterized in an Earth system model? Well, this plot shows how Earth system models have evolved from the original IPCC report to the most recent IPCC report on the right. I've highlighted a couple of things here that demonstrate how the resolution and complexity of climate models has increased over this time period. So in particular, the resolution has gone from about 500 kilometers at the time of the original IPCC report to about 100 kilometers now. So more things can be resolved. And we've also increased the complexity of these models. They include biogeochemistry and chemistry now, which turns them into Earth system models rather than the general circulation models that were originally used in the IPCC. But even with these added layers of resolution and complexity, there are many processes that are still not resolved, but which can significantly affect climate. And these processes have to be parameterized. So to just give an idea of what some of these processes might be, let's think about what's smaller than a 100-kilometer grid box of a modern Earth system model used in CMIP6. Now to demonstrate this, I've chosen to plot a map of the UK. Now, if I overlay the grid resolution of old models and new models, so that's 500 kilometers and 100 kilometers respectively, you can see that the old models wouldn't be able to resolve regional climate within a country the size of the UK. They also wouldn't be able to resolve any of the topography, so that's denoted by these red regions which are mountainous and green regions which are low-lying and flat. On the other hand, the new CMIP6 models do begin to resolve regional climate differences between parts of a country this size. And they can resolve some of the topographic changes within this region. But at the same time, there's a lot of topography that's unresolved. Individual mountains won't be resolved at this 100-kilometer resolution, even though we know that mountains can be significantly impactful for local and regional atmospheric properties and climate. But let's think a little bit more about the components of the Earth system and processes that we know are unresolved and smaller than 100 kilometers, but are climatically important. And I'm going to do that with a few images. So this one shows clouds and surface land use changes. So both of these things are typically smaller than 100 kilometers in size, but are very important radiatively for Earth's energy balance, as well as dynamically and thermodynamically. In the cryosphere, things like icebergs and glaciers are also much smaller than the 100-kilometer grid size of these models. And in the ocean, eddies, which mix properties and affect the large-scale ocean dynamics, are unresolved. So this image is a photo from a satellite off the southwest coast of the UK. And what you can see is these eddies swirling around phytoplankton, which is a biological organism which photosynthesizes in the ocean, is an important part of the carbon cycle of Earth's climate. And so both of these things, these ocean eddies and the phytoplankton dynamics, are happening at scales much smaller than the grid scale of a modern Earth system model. Now you've seen some of the physical processes that have to be parameterized within an Earth system model for it to accurately capture the evolution of the climate. I'm going to let you go into your coding activity for this tutorial, where you'll be comparing output from several different CMIP6 models. And as you do that, I want you to keep in mind those ingredients that we encountered earlier and their differences that they can have between different Earth system models. And as you compare and contrast those different model outputs, keep in mind these processes that might be different within each underlying model.